Hey everyone. So in this video I like to talk about right triangle trigonometry. So when we defined our trigonometric functions, we did so in terms of a circle. Right? We said that if we have some circle of radius r, and we look at an angle of theta in standard position along this circle, then we end up at this point on the circle with an x-coordinate and a y-coordinate. Right? And the y-coordinate can be interpreted as the measurement of this distance here, whereas the x-coordinate can be interpreted as a measurement of this distance. And we said that sine of theta, well, it's the ratio of the y-coordinate on that point divided by the radius of the circle. Cosine of theta is the ratio of the x-coordinate divided by the radius of that circle. And then tangent of theta, well, it's the ratio of y divided by x for that point on the circle. And so because every time we do this, we can sort of fit this right triangle into this picture, and really the ratios we're computing are all ratios of the side lengths of this triangle, we can really apply our ideas of trigonometry to right triangles away from the coordinate plane, away from this circle. Right, really, if I look at what sine of theta is computing, it's computing the side length opposite this angle of theta and dividing that side length by the hypotenuse of that triangle. And similarly, cosine of theta, well, it's computing the ratio of the side length that's beside our angle theta, or adjacent to that angle theta, and dividing it by the hypotenuse of this triangle. And so really, if I have some right triangle, and I have some angle theta in this triangle, well, I can compute our trigonometric functions in terms of the sides of this triangle here, where the opposite side is the one opposite to our angle, and then we have an adjacent side to our angle, and then we have the hypotenuse, which is opposite the right angle. Right, and so in terms of this picture here, sine of theta amounts to computing the ratio where we take the opposite side length, the side length opposite our angle theta, and divide it by the hypotenuse. Cosine of theta takes our adjacent side to our angle and divides it by the hypotenuse. And then tangent of theta will typically, we compute tangent of theta by taking y divided by x, and here in this case, that would amount to taking the opposite side to our angle theta and dividing it by our adjacent side to our angle of theta. So here this is opposite over adjacent. And we can also define our reciprocal trigonometric functions this way. I'm not going to write them all down here, but if you know which functions are reciprocal to which, then you can go ahead and define them in terms of opposite, adjacent, and hypotenuse side lengths to a right triangle. But right, all of this allows us to do trigonometry to right triangles away from the coordinate plane. And so let's apply these ideas to this right triangle here. So I have some unknown angle theta, and I want to evaluate sine of theta, tangent of theta, and secant of theta. And so sine of theta, right, we're saying that it represents the opposite side to our angle divided by the hypotenuse of our right triangle. And so here, again, we don't really need to know our angle theta to do this computation. We just need to know these side lengths and take this ratio. And so we have this right triangle here. We have some missing side that we're going to need to determine, right? We don't know the hypotenuse. And so let's go ahead and compute it. And so x squared, right, the hypotenuse squared should be equal to the sum of the squares of the leg lengths, right? So 3 squared plus 5 squared. And so x squared, that's the same as 9 plus 25, or in other words, 34. And so x is equal to plus or minus the square root of 34. And because we're talking about a triangle here, we're just dealing with the positive option. And so x here, that's equal to the square root of 34, our hypotenuse. And so sine of theta, well, the opposite side to our angle is this side length here, 3. And we're going to divide that by our hypotenuse, the square root of 34. Now let's go ahead and rationalize this denominator. I'm going to multiply by the square root of 34 over the square root of 34 to get 3 square root 34 divided by 34. So that's sine of theta. What about tangent of theta? So tangent of theta, we said, well, that's the ratio of the opposite side to our angle divided by the adjacent side. And so in this case, we could have already computed this without determining that hypotenuse. We would take the ratio 3 over 5. And then the last thing we have to compute is secant of theta, right? So secant of theta, well, this is 1 over cosine of theta, or the reciprocal to cosine of theta, right? So this, we know cosine of theta is adjacent over hypotenuse, and so the reciprocal of adjacent over hypotenuse would be hypotenuse divided by the adjacent side length. And so the adjacent side length is that side length beside our angle. It's 5. And we have the hypotenuse of the square root of 34. This comes out to be, right, so hypotenuse is the square root of 34. The adjacent side length is 5. So this is secant of theta. And so one thing I really just want to point out here is that we didn't compute our angle theta. We didn't need to know the angle of theta. Really, again, these trigonometric functions, they're ratios of the side lengths of this triangle. And so in this case, we really just needed to know the side lengths. Okay, so I've got another 2 examples here. I've got 2 right triangles, and in this case, we've got something a little bit different. We know the angle, and we want to determine some missing side length. And trigonometry can help us out here. So in this first triangle here, we have this angle of 36 degrees, and we know 2 side lengths, and their relationship to this angle is that this side is opposite our angle that we know, and this side, well, this side is adjacent to our known angle. And so what's a trigonometric function that relates all these 3 quantities together? Well, I know that tangent of our angle, tangent of 36 degrees, well, it's this opposite side length, 12, divided by our adjacent side length, which is, well, this unknown quantity. And so here I can solve this for x. I can multiply both sides by x. I have x times tangent of 36 degrees is equal to 12. And then I could divide both sides by tangent of 36 degrees, right? This is some number. And so x is equal to 12 over tangent of 36 degrees. And so that's the exact value of x. And we can run this through a calculator. This comes out to be roughly 16.5166. Right, so you can plug in you can plug in 36 degrees into your calculator for tangent and divide 12 by that number, and this will give you roughly 16.5166. And that's this side measurement here. And then for this other triangle, we have these 3 quantities and we want to figure out one of the side lengths. And so what trigonometric function relates all of these 3 items together? Well, here notice that for this angle, x is opposite that angle. And then we have the hypotenuse of this triangle, 25. And so the trigonometric function that brings them all together is sine. Right? So sine of 53 degrees, it's going to take this ratio, the opposite side length to this angle is well, it's this unknown value x. We're going to divide it by the hypotenuse, 25. And so when we go ahead and we try and get x by itself, we multiply 25 to both sides. We have 25 times sine of 53 degrees. That's going to be the value of this missing side length x. And so we can run this sine of 53 degrees through a calculator. One thing we want to just make sure that we do ahead of time is that our calculator is in degrees mode for this. And when we do this and we take that result and multiply it by 25, we get that x is approximately 19.9659. So that's this missing side length here, and it kind of makes sense, right? The hypotenuse is 25 units long, and that's going to be larger than this opposite side length, which it is in this case. So sometimes, when you're dealing with an applied problem involving angles, you might encounter the phrase angle of elevation or angle of depression. And so really the two images below are good ways of imagining what those statements mean. So let's say I've got a person that's looking upwards towards some birds in the air. This can be an example of an angle of elevation. It's the angle between sort of their eye level, this horizontal line at eye level, and the line between them and the birds. So angle of elevation, this is angle of them looking upwards. Maybe let's say in this different picture, I've got a person now looking down on the birds. And so there's this horizontal line again at their eye level, and the angle of depression represents that angle between the horizontal line and their line of sight towards those birds below them. Okay, so a problem where we might see this is here. An airplane is flying at an elevation of 5,150 feet, and it's directly above a straight highway. And so we've got two cars on opposite sides of the plane, and this angle, there's an angle of depression towards one car of 35 degrees, and an angle of depression towards another car of 52 degrees. And we want to use trigonometry to determine how far apart these cars are. And so, what we should picture here is that there's sort of this highway, and then there's above it 5,150 feet. There is a plane, so maybe the plane's here. And so it's kind of flying straight over this highway. And it's saying that 35 degrees on one side of the plane is 35 degrees downwards. This angle of depression, there's a car. And then 52 degrees on the opposite side of the plane, 52 degrees downwards, this angle of depression. So here's one angle of depression, here's another angle of depression. This one's supposed to be 52 degrees, so maybe it looks down like so. There's another car. And so we want to measure this distance here. And really, that distance, it's the same as this distance here. Right, so here, this measurement, maybe I'll call it D1, and this measurement D2. the measurement between the plane in one car and the measurement between the plane and the other. Oh, I should write D2 here. Okay, and so there's sort of two triangles that we can use here. So one triangle is this one here. Maybe I'll highlight it in green. Hopefully this isn't getting too cluttered. So this is one triangle. And then here's another triangle. And so how can we use trigonometry to determine D1 and D2 and then add these two things together? Well, here, if I look at this angle, you know, what side lengths do we know, or are we trying to figure out in relationship to this angle? Well, we know the opposite side length of this angle, and then we're trying to figure out the adjacent side length. So here, what we really want to compute is tangent of 35 degrees, because we know that that's going to be 5,150, right? The opposite side length divided by this unknown side length, D1. And then similarly, tangent of 52 degrees, well, this is going to be 5,150 divided by D2. And if we can figure out what D1 and D2 are and add them up together, we'll have the distance between these two cars. And so let's go ahead and shuffle things around and isolate D1 and D2 so we can add them together. So I can multiply both sides of this first equation by D1. And then I can go ahead and divide both sides by tangent of 35 degrees. And so, you know, that's some number. I don't know what it is, but you know, we can run it through a calculator to figure it out. And so we get tangent of 35 degrees down here. And again, something I want to emphasize is that this 35 degrees, it's inside this function. It's not multiplied. I can't do any reducing here. Inside this function and outside of this function really don't interact that well. Really, I would have to compute, before anything else, I'd have to compute tangent of 35 degrees, and then I'd have to divide that result from 5,150. And then we could do the same thing for D2 on this right equation. So D2 times tangent of 52 degrees is equal to 5,150, dividing both sides by tangent of 52. Gets my D2 isolated, and so this is 5,150 over tangent of 52 degrees. And so D1 plus D2 is the measurement we want. That's the distance between the cars. This is 5,150 over tangent of 35 degrees plus 5,150 over tangent of 52 degrees. And this is going to be the exact value of this distance, but we can run these quantities through a calculator, and we can end up with the approximate result, 11,378.58 feet. So that's the distance between the two cars, roughly